Hello and welcome to this first of the lectures in the fourth week of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this week, we will look at yet another important fuzzy logic connective, that of fuzzy implications. It is important by itself, also in the context that we are looking at in this course, that of approximate reasoning using fuzzy set theory. We will look at one particular generalization of an implication, that is from the classical implication to the fuzzy implication. To understand this, let's look at when is a given conditional true. Let's consider this statement: if f is differentiable, then f is continuous. Of course, we know that this statement is true. But now, looking at it as an antecedent implying a consequent, that is like P implies Q, in the logical sense, we are questioning ourselves, when is P implies Q true? Let's once again consider this statement: if f is differentiable, then f is continuous. So now, let's pick up a few examples of functions f. Consider for instance the function x squared. We know this is differentiable and this is also continuous. Let's look at the function mod x. We know that this is not differentiable at the point 0, at the origin, but however it is continuous on its entire domain, which is R. So now, given these two examples, the first example, it reinforces the conditional that whenever it is differentiable, it is continuous. The second example, does it contradict the statement that f is differentiable implies f is continuous? No, it does not contradict, because the function itself is not differentiable. Let's consider another function, f of x. So it's 1 if x is less than or equal to 0, and 2 if x is greater than 0. Now, this function clearly is neither differentiable nor continuous. Now, does this example contradict the statement differentiability implies continuity? Once again, it does not. So, only thing that could contradict this statement is if you could have a function which is differentiable but not continuous. However, we know that such a function or R does not exist. Now, let's consider in some sense, the converse of this statement. If f is continuous, then f is differentiable. That means now we are looking at the statement C implies D. Once again, let's consider the function x squared. We know it is continuous. We know it is differentiable. So it appears that the statement continuity implies differentiability looks true given this example x squared. However, let's consider the next example, f of x is equal to mod x. It is continuous, but as we have seen, it is not differentiable at the origin, so it is not differentiable over its entire domain of R. This immediately tells you that this statement is no more true. That means we have an example where the antecedent is true, but the consequent is not true. Thus, this conditional statement is actually false. So if you look at it, if you ask the question, when is P implies Q true, we see that whenever P is false, it is true, because immediately the antecedent of the conditional statement does not come into picture, or it is true if the consequent is true. So that is how we have captured it. P implies Q is true if either E is false or Q is true. Now, if you are looking to generalize a classical connective to fuzzy logic connective, we have seen that we have to maintain the truth table of the corresponding classical logic connective. On the 0-1 set, the truth values of the classical logic connectives, if you take the implication, then the truth table of the implication looks like this. So note once again that P and Q, they can take either 0 or 1. and P implies Q, again it can take either 0 or 1. This is the truth table of the classical implication. We know that in classical logic we have only these two truth values indicated either with these two symbols or as 0, 1. In fuzzy logic, these truth values range over the entire interval 0. So now we need to generalize this connective, the classical implication, on the set 0, 1 square to 0, 1 to the interval 0, 1 square to 0, 1. Just like how we have done in the case of T-norms, negation, and other such connectives. Okay. Let's look at what was the very first fuzzy implication that was proposed, or what could be considered as the first fuzzy implication that was proposed. It was way back in 1923, almost 100 years from before today. A Polish logician, Jan Łukasiewicz, proposed this in one of his papers, and this is in some sense a good translation from what would have been written in a Polish language, wherein he said, the variables P, Q, let them stand for any real numbers in the interval 0, 1, including the limiting values of that interval. The formula P using the symbol Q equals the number 1 if P is less than or equal to Q. That is, P, what we would called as implication, P implies Q, is 1 for P less than or equal to Q, and it is 1 minus P plus Q whenever P is greater than or equal to Q. And you can see that when P is equal to Q, they satisfy both these conditions. But at that point, they actually coincide. It is 1. So this perhaps was the very first fuzzy implication, a multi-valued implication that was proposed, and it was proposed almost a century ago to the day. This is what we know today as the Łukasiewicz implication in the fuzzy set theory literature. And when you translate it in terms of xy variables over the unit interval, this is how it looks like. This is one way of writing it. This is how Łukasiewicz had written, and it could also be written equivalently in this form. If you were to look at fuzzy implications themselves, say from early 70s or mid 60s, when fuzzy set theory started catching up, you could perhaps trace back its origins to parallel or independent origins. First, as a truth space fuzzy relation. We are yet to see about fuzzy relations, which we will take up in the next week. But as a truth space fuzzy relation, this is how many of the early works on fuzzy implications, especially during the 70s, explored this particular connective. And remember, these were actually employed in fuzzy if-then rules, which play an important role. They are an important component in approximate reasoning. We have seen this in some of the early lectures, how conditionals play a role and how we will interpret conditionals capturing knowledge in this course as fuzzy if-then rules. So they were actually used to capture fuzzy if-then rules. Similarly, they were also explored as a logical connective, like how we have seen about T-norms so far. This was also a way fuzzy implications were explored. So they have had two independent and parallel origins and exploration. We will of course take the second approach for the moment, but as you see that it plays a very important role when we are talking about approximate reasoning using fuzzy set theory. Well, let's try to come up with a generalization from the classical implication to the fuzzy implication. It's the same classical implication truth table, but only just slightly rearranged so that we would see how the definition has come into existence. So we say a function I, a binary function, binary operation on the unit interval 0, 1 to 0, 1, We call it a fuzzy implication if it satisfies these three properties. Firstly, it should be decreasing in the first variable. Now, what has led to this observation? Look at this. If you fix the second variable to be 0 and increase from 0 to 1, you see that the overall truth value moves from 1 to 0. It actually decreases. If the second variable is fixed at 1 and if you increase, it remains a constant. But in the case when the second variable is 0, as you move from 0 to 1, what we see is that actually the overall truth value decreases. So this is what has been captured in this, as saying that an implication operation is expected to decrease in the first variable. And once again, it is not in the strict sense. Essentially, it should be non-increasing. What about in the second variable? Let's fix the first variable, for instance, 0 here. And as we increase the second value from 0 to 1, it remains a constant. However, if we fix the first variable to be 1, and if we move from 0 to 1, we see that it is increasing. So this is what is captured as saying that it is increasing in the second variable. Note that this is in stark contrast to what happens in TNOMs, where it is increasing in both the variables. Finally, we ask that all these boundary conditions are satisfied. Essentially, we are rewriting the truth table in this form. I of 0, 0 is 1, I of 1, 1 is 1, 0, 1 is 1, and 1, 0 is 0. Notation here. We will use the script I to denote the set of all fuzzy implications henceforth. Okay, next, let's try to decode this definition. So what we have here in symbolism, I is decreasing in the first variable and increasing in the second variable and satisfies these four boundary conditions. We have seen that when you're looking at classical logic connectives, this is your X, this is your Y, then what we are looking at is what happens at these points. So this was what is defined in the case of classical logic connectives. So on these vertices of the unit square, the classical logic connectives are defined. Now what we want to do is we want to extend it to this entire unit square. Now let's look at a 3D view of a fuzzy implication. Once again, note, we have seen that in the definition of fuzzy implication, we have not asked for any algebraic property like symmetry, associativity, or even neutrality. So we have kept the definition extremely simple. We only abstracted the properties that we are able to see in the truth table. Now, in the case of TNOMs, the perspective that we took for the plots was from the origin to 0, 0. However, in the case of fuzzy implications, the perspective that we take is keeping the point 1, 0 as being the nearest point to us, and we take this perspective because this is the perspective that gives maximum information about the implication from the graph of the implication. Clearly, it's a two-variable function, which means the graph is in 3D. So you see the origin 0, 0 is here, but the closest point to us in terms of our perspective, what we see is the point 1, 0. So now let's look at how to understand the axiomatic definition of a fuzzy implication. First, let's look at the boundary conditions. What does it say? At 0, 1, it is 1. This is y is equal to 1 and x is also x is equal to x is 0 here, y is equal to 1 here, so it is 0, 1. At I of 0, 1 is 1, and this is y is 1 here and x is also 1, so I of 1, 1 is 1 here. So on these 3 points it is 1, and this is the point x is equal to 1 and y is equal to 0. So I of 1, 0 is 0. So these are the 4 vertices that have been fixed by the classical implication for us. Now, what happens with the monotonicity part? So it says it is decreasing in the first variable. That means if you fix a y, that means if you are on this axis, we have fixed a y and move along this direction from x is equal to 0 to 1, we expect that it should be decreasing. Similarly, if you look at the second variable, that means if you fix the first variable, fix an x, and if you move along the y direction from as y increases from 0 to 1, we expect that this should be increasing. So essentially, this is all that we require of a fuzzy implication. At the corners of this unit square, we fix up the boundary condition and we say it is decreasing in the first variable and increasing in the second variable. Now, what is interesting is these 4 boundary conditions can be actually reduced to just one of them, I of 1, 0, 0, and you could actually come up with an alternate way of or equivalent definition by adding these 2 properties. And note that these properties can be obtained from the previous 3 boundary conditions. It's quite simple. Let's look at what they mean to us. So what we have is the boundary conditions. I of 0, 0 is equal to I of 0, 1 is equal to I of 1, 1 is equal to 1. Now, this says I of x1 is equal to 1 for any x element of 0, 1. Now let's look at I of x1. Now, since x belongs to 0, 1, so we know that 0 less than or equal to x less than or equal to 1. Now, if you take I of x1, we know that I is decreasing in the first variable, which means I of x1 is greater than or equal to I of 1, 1. Because as x1 is bigger than x, I of x1 is greater than or equal to I of 1, 1. But this is equal to 1. And we know that the function I itself is from 0, 1 square to 0, 1. So nothing can be greater than 1. But if you would want, you could also bound this like this, which is 1. So from here it is clear that I of x1 is equal to 1 for every x element of 0, 1. So this is what we have seen here. Similarly, if you look at I of 0, 1, once again, y is between 0 and 1. Now we know that in the second variable it is increasing. So now if you take I of 0, 0 less than or equal to I of 0, y is less than or equal to I of 0, 1. But note here, I of 0, 1 is 1, I of 0, 0 is 1, essentially stating that this is also equal to 1. So from these 3 conditions here, we actually get that I of x, 1 is 1 and I of 0, y is 1. Of course, I of 1, 0 cannot be obtained from anything else, not from the monotonicity and the other boundary conditions. So this has to be preserved. What does it mean in terms of geometry? It means that we are talking about these boundaries. Look at this. This is when x is equal to 0, and as you go along the y direction, it is 1, that is this boundary. And this is y is equal to 1 boundary. And as you walk along this boundary from x is equal to 0 to 1, we say that it is 1. Because of monotonicity, these 3 points can only be linked at the height of 1. So geometrically, if you see, the left boundary is 1, the top boundary is 1, and the point closest to you, or essentially the right bottom point, is at 0. This is all that we insist on a fuzzy implication, and this also comes about because of the boundary conditions and the monotonicity that we see here. Having this kind of a geometric perspective helps us in graphing a given implication and also be able to visualize any given fuzzy implication, because some of these things are actually fixed for us. And it also makes it interesting to construct implications with some specific properties. Let's look at a few of them. We can ask the question, is there a smallest fuzzy implication? Smallest in the sense of the pointwise ordering of functions. We know this, that when x is equal to 0, this region, it is 1, and y is equal to 1, it is 1, and at this point it is 0. Nothing else is specified. Of course, Overall, we know that it should be increasing along y and decreasing along x, but nothing else is specified. So if you ask the question, what could be the smallest fuzzy implication? Then we keep these and then try to push the values in the rest of the region as small as possible. How low can we go? Clearly, we cannot go below 0. So essentially, we just make it 0. How would the graph of this fuzzy implication look like? It would look like this. And in the literature, this is typically indicated by the implication symbol I0, essentially saying, okay, this is the least, the smallest fuzzy implication that you could have, where it is 0 almost everywhere except on the left and the top boundary where it has to be 1. Similarly, we could ask the question, what would be the largest fuzzy implication? Once again, the left and the top boundaries are fixed at 1 and the point closest to us, which is 1, 0 is 0. Now, if you want it to be largest in terms of pointwise ordering, then we want this function value to be as high as possible. Clearly, it cannot go above 1. So what we do is, in rest of the places, except at this point, we make it 1. So the graph of this largest fuzzy implication would look like this. It's almost everywhere 1, except at the point 1, 0. At x is equal to 1 and y is equal to 0, which is this point, it is 0. Elsewhere, it is 1. And typically, it is denoted as I1. These two notations actually come from considering set of all fuzzy implications as a not just as a poset with respect to pointwise ordering. It can be shown it is also a lattice, but perhaps we may either see it a little later when the situation warrants, or maybe not also. Right. Now let's look at why in the literature they have gone for this particular generalization. Once again, I'm going back to the definition. That means it is decreasing in the first variable and increasing in the second variable, and these 4 boundary conditions. Now, why this generalization? Well, clearly, we have seen that we have got it from the truth table of the corresponding classical implication. There's also another reason. If you maintain only this, note that we have not asked for commutativity. Obviously, we don't have commutativity because the type of monotonicity that we have is a mixed monotonicity. It's not the same. We have not looked at some form of associativity. We have not asked for it to be having a neutral element. None of those algebraic properties we have asked, because this definition captures the essence of the classical implication truth table and allows us to have a plethora of operations which are useful in different contexts, especially from the point of view of approximate reasoning. It should also be noted that in early days, many other properties were expected of fuzzy implication, but slowly people realized that the freedom that having these basic axioms set alone as part of this definition allowed them, especially in different contexts. Hence, currently in the literature, this is accepted as the standard definition of fuzzy implication. Finally, we can also show that these properties are mutually independent. For instance, let's look at it. These are the 5 properties that we could consider. I00 means whether at I of 00 it is 1, at I11 means whether I of 11 it is 1, and clearly I of 01 will be 1, and we are looking at I of 10 whether it is 0. Let's look at this function, max of 1 minus x, min of x, y. What we see is this function has these 4 properties except for decreasing in the first variable. Now, this is not very difficult to see. Let's look at this function I of x, y. It's max of 1 minus x, min of x, y. So what we want to show is that this function is actually not decreasing in the first variable. So for this, let's fix the second variable to be 0.6 And the first variable, let's move from x1 is equal to 0.1 to x2 is equal to 0.6. So let's look at what is I of x1 comma y. Now this is max of 1 minus x, x1 is 0.5, 1 minus x1, that is 0.5 comma minimum of 0.5 comma 0.6. Now this will be max of 0.5 comma 0.5, which is 0.5. What about I of x2 comma y is max of 0.4 plus 1 minus x2 comma min of 0.6 comma 0.6, which is max of 0.4 comma 0.6, which is 0.6. Now remember what we want is, as fixing y, we are seeing that x1 has gone up to x2, fixing y, and what we want is the implication should actually be decreasing. That means I of x1 comma y should be greater than or equal to I of x2 comma y, since x1 is less than or equal to x2. This is what we want for I to be decreasing in the first variable, but as you can see here, it is actually increasing. It can be easily verified that if you fix x here, as you increase y, it will increase. I of 0, 0 is actually 1. Put 0 here, it is max of 1 comma something, it should be 1. If you put 1 here, this will be 0, but min of 1 comma 1 is 1, so max of 0, 1 is 1. At 1 comma 0, max of 1 minus 1 is 0, minimum of 1 comma 0 is 0, it is max of 0 comma 0, so I of 1 comma 0 is 0. You can also be seen that I of 0, 1 is 1. You put 0 here, essentially it just becomes 1. Now, if you consider this function, almost the dual of what we have seen earlier, it can be shown that this function is decreasing in the first variable, but it is increasing, it is not increasing in the second variable. Once again, we can take some selective values. For instance, if you take the value x is equal to 0.4 and y1 is equal to 0.4, y2 is equal to 0.5, I think you can easily see for these values that it is not increasing in the second variable. Now, if you consider this function, I of xy is given like this. Once again, you can see that it is decreasing in the first variable, increasing in the second variable, has the other properties, except that at I of 0, 0, it is not 1. When y is less than 1, that means the moment y is 0, it is 0. And if you consider this function, we see that I of 1, 1 is not 1, because when x is 1, it is 0. Finally, this simple function shows that you can have all the first 4 properties, but I of 1, 0 is actually not equal to 0. So you see here, the way we have abstracted these properties, they are also mutually independent. Okay. Just as in the case of T-norms, where we had 5 basic T-norms, the drastic, Lukashevich, product, minimum, and the Fodor T-norm, the nilpotent minimum. Here also, we have what we would consider as basic fuzzy implications, but not just 5 of them, but 9 of them. And if you add also the smallest and largest fuzzy implications, it comes out to 11. So these are considered as basic, as we will see later on, just like how these basic T-norms played a role in characterization and representation. These fuzzy implications will also play a similar role both in theory and application. To better appreciate these formulae, let's look at how the graph of these fuzzy implications would look like. Okay. So now, the Weber implication is given as this. The graph that you see on the screen is the skeletal graph of a fuzzy implication, where we have only specified how it should be on the left boundary and the right boundary, and also at the point 1, 0. This was the largest fuzzy implication that we saw. Weber implication is a slight modification of this. It's 1 everywhere except at this point 1, 0. But when x is equal to 1, we make it the identity function. So essentially, I have 1 comma 0 0, I have 1 comma 1 is still 1. And what we are doing is when x is equal to 1, we're just making it y. So this is the Weber implication. The Gödel implication, what it does is, in some sense, it presses a part of the roof onto this line here. So this is how the Gödel implication will look like. When x is less than or equal to y, it is 1, and anywhere outside of this domain, it is actually 1. The Gödel implication can be looked at as somehow trying to make this graph look continuous. Of course, it cannot be continuous because at 0 0 it is 1, but when x is not 0 but y is 0, we see that it is actually 0. So you have a point of discontinuity at 0 0, but otherwise in other places it is 1. And the formula is given like this. In the case of Gödel, when x is greater than y, it is y. In the case of Gödel, it is y by x. And this is how the plot of this fuzzy implication would look like. Now, this is what we call the Fodor implication, where you have 1 above the diagonal. Essentially, x is equal to y is the diagonal. So above the diagonal, you have 1. And below the diagonal, to the right of the diagonal, this is how the graph looks like. From here, in some sense, a continuous completion you could think of as would give you the Lukasiewicz implication, but not necessarily in the same way, but just only in terms of taking a visual cue. Finally, from this Fodor implication, you could also get other kinds of implication. For instance, extend it without having 1 in no other place other than on the left and top boundaries. Extending it, you would get what we call the Klein-Dienz implication. Of course, there is the Reichenbach implication. And if you push this part down, you would get the Rescher implication. So earlier here, outside of the diagonal, we had some values. So all it says is above the diagonal we have 1 and below the diagonal we have 0. This is another important implication proposed by Jager, and this is how it looks like. Of course, these will keep appearing again and again, and we would slowly get comfortable with these formulae. But these are not the only kind of implication. I said these are the basic fuzzy implications which keep appearing again and again, but you could also have fuzzy implications of this type. Okay, a quick recap of what we have seen in this lecture. Once again, we have made a balanced extraction of properties of classical implication into an axiomatic definition for fuzzy implication. We have also seen some geometric perspective, especially of the basic fuzzy implications. Now, what lies ahead in the next few lectures to come during this week? We will look at an algebraic and analytic perspective of fuzzy implications themselves. We will look at constructions of fuzzy implications which lead to families of fuzzy implications. And we will also look at some functional equations involving fuzzy logic connectives, specifically implications. In the next lecture, we will look at some desirable properties of fuzzy implications. As was mentioned during this lecture, initial days, the definition of fuzzy implication included many other properties, especially neutrality and exchange principle, which we will see as properties which are desirable, of course, but may not find a place in an axiomatic definition of fuzzy implication. And there are no more such desirable properties. Some of them which are useful considering the context of this course, the focus of this course, we will deal with those and those alone. Rest of them, as and when required, perhaps we will see. Finally, a good resource for what has been covered in this lecture is the book of fuzzy implications. You would find more examples, more plots, and also some interesting properties dealing with even the basic fuzzy implications, which we may not be able to cover in this course, because we would want to stay true to the title of this course, that of approximate reasoning using fuzzy set theory. So we'll pick the content, keeping that in mind, keeping that as a focus in mind. But there are also many other very interesting things that you can discuss about fuzzy implications. And at least definitely what has been covered in this lecture, you will find that and a little bit more in terms of explanation and some interesting examples in this book on fuzzy implications. Thank you for joining me in this lecture and hope to see you in the next lecture.